Welcome back to the NPTEL lecture course on tectonics and geodynamics. So this is lecture 14, and this time we're going to talk more about the consequences of motion on a spherical Earth. And in the context of this, we'll have to think of what happens when we combine rotation vectors, right? Exactly what would be of what use is it in the context of plate tectonics, and how can it actually help us to identify the motion that takes place along plate boundaries in various parts of the Earth, along various kinds of plate boundaries. Okay, so the part that we are going to be concentrating on obviously is going to be just this part here, based upon the combination of rotation vectors, what exactly happens when we actually combine them. And just to get back to what we were discussing in the last class, right? What we just now, it's important for us to understand exactly what the little values that we put in actually what they mean. So it's very easy to lose sense of why exactly we are writing out a particular equation or what we are calculating, right? Why exactly we're doing that. The idea is that for any pair of plates, so let us say there are two plates which are adjacent to each other. So these two plates may have a small transform segment between them. So if there is a transform segment between any two parts of a plate boundary, we can use that transform segment, so any two transform segments if they are suitably separated apart, and we can draw longitudes perpendicular to those transform segments, and where they intersect on the surface of the Earth would be the position of the Euler pole of rotation for those pairs of plates. Now, as I said, this is just one of the various mechanisms by which we can actually find out the position of the Euler pole for any pair of plates. You can just as well do it by using by monitoring how the linear velocities are actually varying along a particular plate boundary, and you can actually see where the plate linear velocities tend to zero. So where it tends to zero, that must be the position of the Euler pole of rotation. So this is something that these are mechanisms that we can use to find out the position of the Euler pole. Now, once the position of the Euler pole of rotation has been found out, then knowing that, we can always characterize what the linear velocity would be at any particular point on the plate boundary, and from that known point, we can back calculate to get the angular velocity that characterizes all movement along that Euler axis of rotation for that pair of plates. So for a particular pair of plates which are rigid with respect to each other and they're moving with respect to each other on the surface of a sphere, there will be one fixed Euler axis of rotation. There will be two poles, a positive Euler pole and a negative Euler pole, and there will be an angular velocity that will be applicable to all points along the plate boundary. So this is what is given to us. Once that is given to us, what we can measure, because it's not humanly possible to measure and document what the linear velocity would be along every point along a plate boundary. Once we know the angular velocity and the location of the Euler poles, we can calculate, when needed, we can actually calculate the linear velocity of any point on a plate boundary, right? Once we are given those values, because the angular velocity and the position of the Euler pole, these are known. Once these two things are known, we can calculate the linear velocity for any point on a plate boundary, and that is what we saw in the last class. We saw that it's possible for us now, once we're given these values, to characterize exactly the magnitude of the velocity as well as the direction in which it is operating, right, at any point on a plate boundary. Now, given this is important, but it also tells us what we don't yet know. The problem is that, we can actually, let us say for the African and South American plates. Now, we've actually shown this here in this red mark actually shows the boundary between the South American and African plates, and it's shown very crudely. But if you remember the actual nature of the boundary, in many of these places, these are displaced by transform faults. So there are transform faults, large transform faults with large displacements, which displace the mid-oceanic ridge, the mid-Atlantic ridge in this case, between the South American and the African plate. And using those transform segments, it is possible for us to find out the Euler pole of rotation. Along various parts along this plate boundary, the linear velocity has been measured, and from that, when you actually back calculate, you can actually get the magnitude of the angular velocity. So we know it for this pair of plates. So we know it for between the South American and African plate, for example. On the other hand, if we want to find out what is the relative motion of the South American plate with respect to the Scotia plate, let's say this one here, or with respect to the Antarctic plate to the south, in many cases there may not be sufficient information, right, or there may not be enough information for us to find out what the Euler pole of rotation is for a particular pair of plates, or what is the angular velocity associated with those pairs of plates, and that's necessary. In fact, to understand how motion takes place between plates on the surface of the earth, it is important for us to know what the angular velocity and what the angular velocity of associated with any particular Euler pair of plates is, and it is also important for us to know what the Euler pole of rotation, where the Euler pole of rotation is located, right, for each pair of plates that we are concerned with. So therefore, this information is needed for us. Now, how do we actually get this information? Because not all boundaries may have segments that are characteristic and may enable us to identify the locations of the Euler poles of rotation. It's completely possible that this is something that is not known to us. So how do we actually begin to analyze this? So we can now rephrase the problem. How can we determine the Euler pole and angular velocity of plate C, let us say, with respect to plate A? The angular velocity as well as the Euler pole of rotation of plate C with respect to plate A. Okay. So given the Euler polar positions, when we are given the Euler poles of positions or velocities of plate C with respect to B and plate A with respect to B. So now we've been given some information, then how do we actually begin to calculate exactly what the third plate orientation would be? It means that if you've got three plates A, B and C, we've been given the Euler, the location of the Euler pole of rotation for plates A and B, and let's say for plates B and C, but we don't know what the location of the Euler pole of rotation for plates A and C would be, and we don't even know what the angular velocity would be. And for all the other two plates, right, the other two in this system, we have got that information, we have that information. So then in that case, let's get around to thinking what it would be. So let's now think of how to solve this problem. Now angular velocities are vectors, and therefore they should follow all the rules of vectors. And if they follow the rules of vectors, then we can actually write it that the angular velocity of plate A with respect to C, right? This is something that we want to find out, right? We would like to find out what the angular velocity of plate A is with respect to, write it a little better. Okay, so we need to know what this is. Now, what are we given, right? What kind of information are we given? So we have three plates, let's say A, B and C, right? And this is what we are not given, right? So which means then we can actually think of the things that we are given, right, between the plates. So let us say that the values that we are actually given, the things that we are actually given would be with respect to plates A, B and B and C, right? This is something that is given to us. So let us say that for these we can depict it this way. So if we write it as the rotation vector, then we talk about its magnitude, right? We talk about the latitude of Euler pole and then the longitude of the Euler pole Okay, so we have these things given to us. So let us say the relative velocity, right, let us say of plate A with respect to plate B, right? So this is the vector we have. It has a magnitude which we will just use it. I mean, when you're actually typing, then you can actually use the bold signal from here. You need not put the arrow on top to demarcate the vector. In this case, the magnitude will simply show it in this particular way. And we'll say that for plates A and B, this is the magnitude of the angular velocity, right? The angular velocity of plate A with respect to B. Let us say the latitude of the Euler pole is also known to us. This is lambda BA, whereas the longitude is equal to phi BA, right? So this is the writing that we'll use, right? To actually, these are the terminology that we'll use to solve, to work out how to calculate what we want. Similarly, right, if we have the relative velocity of B with respect to C, B with respect to C. So this is the vector, its magnitude we can just say omega B with respect to C, right? So omega B C, you could say. The latitude of this pole would be lambda CB, and the longitude, pardon me, we write it as phi CB. Okay. So this is what is given. What do we not know, right? We do not know omega A with respect to C. Now this is something that we don't know, right? This is what goes in here. We don't know it. So what we need to find out is the value of omega A with respect to, we need to find out the magnitude of omega A with respect to C. We need to find out the lambda of lambda CA, which is the latitude of the positive Euler pole of rotation, and we need to find out phi CA, which is the longitude of the Euler pole of rotation. So these are the things that we do not know, right? This is something that we need to find out. So once again, stating the problem, we have three rigid plates A, B and C, right? If we have three rigid plates A, B and C, then in that case, we have been given the rotation vectors, right? The magnitude of the fully characterized rotation vectors means the magnitudes, right? And the latitudes of the Euler poles of latitudes and longitudes of the Euler poles of rotation between plates A and B and between plates B and C, right? What we need to find out would be the vector that is concerned with the the angular velocity between plates A and C, right? So this is something that we need to find out. Now, since these are vectors, however, we can actually use the same sort of principle. So omega A with respect to C, this vector, we can actually represent it as omega, right? So B with respect to C plus omega of A with respect to B, right? Just the typical way we write vectors. So if we can actually solve it this way, then we can actually resolve the whole thing more easily. Now the first thing to realize is that these actually carry a meaning. Now since we know these are vectors, right? So omega of B with respect to C is equal to minus of omega C with respect to B, right? Similarly, omega A with respect to B is equal to the minus of omega B with respect to A. Now it means then that if we substitute these values, right, into this equation, right, if we substitute here, then we can rewrite this equation and say that omega C with respect to B plus omega B with respect to A plus omega A with respect to C must be equal to 0, right? So basically what we are doing is taking all of this to this side of the equation and then substituting with these values. So once you do this, you get this. Now what does this actually mean? Now when you have three vectors, right, which add up to 0, this implies, right, this implies that these must be coplanar. Okay. So in other words, if we actually now think of a plane which is cutting through this sphere, right? Let us think of a plane which is cutting through this sphere, then we can actually have one here, one here, one here. So we can call them different things, right? So if we call this omega A with respect to B, this will be, let us say, omega A with respect to C, and this would be omega of B with respect to C. So it means all of these lie on a plane, right, which passes through the center of the earth this way. So all three of these vectors would lie on one plane, right? So whenever three vectors add up to give you 0, it means that they have to be coplanar. Otherwise, you cannot get this. Now, given this background, then how can we actually use this? How can we actually use this to resolve the problem that we've set up for ourselves? So let's now go on to this blank piece here, and what I'll do here is actually draw this as a draw a circle, right? Might not be a very good circle. Just imagine this is a circle, which represents the earth. Let's say that is north, that is south, right? And then let's say this is the center of the earth. Let's find out if I can make this circle a little nicer. So let's see. Oh my god, it's wiped out the whole thing. So it means that I have to draw it again. Okay, slightly nicer. Okay, so let's say this is the center of the earth here now. This is the center of the earth here. Now, what we can do is actually to set this out, right? Is to actually set this out in terms of 3 coordinates here. So we will now represent this, right, in terms of Cartesian coordinates. So we will represent this in terms of a Cartesian coordinate system and represent all the vectors on this coordinate system. So the equatorial plane, so let us say that this is my equatorial plane. So okay, so this is my equatorial plane, and on this equatorial plane, let us say that this would be my y-axis. Let this direction here be my x-axis. So this is my y-axis, this is my x-axis, and perpendicular to the equatorial plane passing through the north polar of the earth is my z-axis. Okay, so I now depict it in this particular manner, right? Anything I show would be in this particular manner here. So now in this configuration, so what I've done is now the equatorial plane, right, is the xy plane, right? The first thing to keep in mind, the equatorial plane is the xy plane. Now on this xy plane, let x, right, pierce the Greenwich meridian. So where it pierces this point, so x here is piercing the surface of the earth at that point. So the Greenwich meridian, the longitude that represents the Greenwich meridian, passes through here. So just to show you what I mean, right? So let's have a red blue circle here. Okay, so this, in other words, is the Greenwich meridian, i.e. it's 0 degree longitude. Okay, so that is essentially what I mean here. So this point, it pierces it at the Greenwich meridian. Obviously it means that this point must be 90 degrees, plus 90 degrees, let us say. This point would be minus 90 degrees, right? So and all points here would have longitudes which are greater than 90. The magnitude of the longitude would be greater than 90. So this here, obviously, because it's an equatorial plane, so this is a right angle. So this would be the angle between the z-axis that we have here, right, and this longitude here. So now, given the what else are we actually supposed to, what are we given on this? We've been given the values of different points here, but now we need to actually think in terms of how to resolve this. So let's actually treat this with a different color. Let's take this. Let us take, right, any one of these, right? So as my point here. So let us just say that this point here, right, it represents, say, omega of b with respect to c. Okay, so let us say this is the arrow that represents omega b with respect to c, and let's say that its magnitude is proportional to this piercing point here. Now I want to represent the magnitude that we've got. This is this line omega, right? This is the actual length. It represents the actual length of that is the magnitude of the angular velocity. Now this magnitude of the angular velocity has to be represented in terms of 3 coordinates, right? So it has to be represented in coordinates in x, y, z space. Okay, so what we can actually say is that if we now resolve this once, because we know, we've actually seen that that according to the formula, right, the whole idea is that if you've got omega a with respect to c, this even magnitude wise, right, omega a with respect to c, right, so we know that this must be equal to this with respect to b. So this is there, the magnitudes have to equal up. So for each of these now, if we take the components of omega along the x, y and z directions, that should actually enable us to be able to actually correlate exactly what we're seeing here. So if I'm now, let us say, taking that magnitude, so say omega b with respect to c, this is the actual magnitude is omega b with respect to c. This is the magnitude of the angular velocity. So this is proportional to this particular length. Now how much would this value be if I now find out the x, y and z coordinates, right, x, y and z coordinates of this, right? So we can say I project this particular length onto the equatorial plane. So this is actually the length omega bc, which is this, is actually being projected onto this part here. Now this angle here that is shown here, right, this has a particular value that must be proportional to the latitude, right, of this particular Euler of the Euler pole here, right, for this particular combination. Similarly, right, if you now actually look at the length, the projected length, this is the latitude that we've got here, right, and if you look at this angle, this is the longitude. So this part here must be equal to lambda cb, this angle, and this angle here, right, on the equatorial plane, this must be equal to phi cb. So you've got, sorry, I mean, maybe I should make it look a little more distinct. This angle here, this is equal to lambda cb, and this angle here, right, this angle here on the equatorial plane, this angle here is equal to phi cb. Okay, so this would be the x and y axis, right, of x and y components, right, of omega b with respect to c. Similarly, we can get components for this, right. So for omega a with respect to b, also there would be components like this, right. So omega bc, for example, the components that we have for omega bc, the components would therefore be x cb, y cb and z cb. I don't know where this came from. Wait a minute. Oops. Show why this came in. Okay. Now, similarly, when we have omega a with respect to b, so you can actually write it in the form of x ba. You will have y XBA, YBA and ZBA. So these would be the three components here. Similarly, this would be the case also for the one that we need. So omega AC must have omega XCA, YCA and ZCA as its components. Now, since we are representing this as Cartesian coordinates, then the total XCA value must be the sum, right, because we've got this relationship already here. So XCA must represent the sums of these two. So of the X coordinate components of omega AB as well as the X component of omega BC. In other words, then XCA, right, XCA itself, this can be written as the sum of XCB plus XBA. Similarly, YCA can be written as the sum of the Y components of CB and BA, and just the same for the Z component, that would also be the sum of the Z components of CB and BA, right. So if we just add these values, we can get the X, Y and Z values for each of these components here directly. Now, how do we get the X, Y and Z components? So to get the X, Y and Z components, right, we can actually write down XCA. Now, what would XCA be? It would be, first of all, the first thing that we had was X. Let's go back to the previous one. It was X. It was the sum of XCB. Now, XCB, what is XCB? It's the X component of CB is this line. So, if this is omega BC, then when you project this onto the equatorial plane, right, you get this particular line which is a part of this triangle, and when this is projected onto the x-axis, this length is actually equal to XCB. So how do we get this length? First of all, we have to get this length. What is this length equal to? This length when we're doing this. So this length is omega, this is equal to omega BC. Let us say this is omega BC. This is the latitude. So this line here would be the cos of the latitude. So the length would actually be, this would be omega CB, right, cos of the latitude here, right. So omega CB cross of the latitude. So let's go to this. This would be omega CB, right. So omega CB cos of latitude CB, right. This is the first part we have. So that's not also complete, because if this is omega CB, this is the cos of the latitude, would actually give me this length. But this is not my x component. My x component means that this length has to be projected onto the x-axis. So it has to be projected down here, and it must be equal to the cosine. So this length into the cosine of this angle. But what is this angle? This angle is obviously the longitude, right? It's actually the longitude of this particular angle. So this point is just the longitude of this particular angle, because it's in the same, this is in the same vertical plane. So it must be the longitude here. So this angle is phi CB. So it will be the cos of phi CB. So it means that this would become sum of cos of phi CB. So you actually make it omega C. So CB really, XCB is equal to omega BC cos of lambda CB into cos of phi CB, right. This is what we get, would be a writing out the value of XCB. Similarly, the next value that we have is the writing the value of XBA, right, and you used similar logic. So XBA would be omega BA, the magnitude omega BA, into the cos of the longitude of the BA vector, right, which would be equal to lambda BA, latitude of the vector, into the cos of the longitude of this vector, which is phi BA. Okay. So, this would mean that we can calculate XCA directly, because all of these values are actually known to us, they are given to us. Similarly now, if I had to take YCA, right, what would this value be equal to? Now, YCA is the Y component of the same thing. So, now I took the X component along the X axis. Now, suppose I had to take the Y component of CB, for example. What would it be? The Y component would be the perpendicular that I dropped from here onto this part here, right? So, in this case now, it would be just the opposite of what we used here. So, initial part is same, we get this particular line, right? We get this point, you project omega CB onto this equatorial plane and then project this onto the Y axis instead of the X axis. So, instead of the cos of this angle, now you have to take the sine of the longitude. So, it will be, the first part of it will be the same. So, it will be omega CB cos of lambda CB. So, that would remain the same, right? It would remain the same here. But on the equatorial plane, you have to take the sine of the longitude. So, this is what it would become. And this, on the other hand, would be the same here, omega BA cos of lambda BA sine of phi BA. So, this would give me the Y component. Now, what about ZCA? Now, ZCA is equal to, obviously, ZCB plus ZBA, right. So, in this case, it is the sine component. Now, from here directly, all we need to do is to drop a perpendicular onto the Z axis directly from this point, right. And so, what is this angle? This is 90 minus, this is 90 minus the longitude here. So, 90 minus the longitude. So, for each of these cases now, so ZCA, so this would become omega BC, right, sine of lambda CB plus omega BA sine of lambda BA. Just this would actually give us the x, y and z coordinates, right, of omega c with respect, or a with c with respect to a. Now, or a with respect to c. So, we can get that. How do we get the magnitude? Now, it is a very simple affair. So, omega, the magnitude of a with respect to c, right, this would just be equal to the root mean square of, all we have is x of CA square plus y of CA square plus z CA square. So, this will give me the magnitude that we have got. Now, so the first thing we found out what the magnitude of the angular velocity would be. The next thing that we need to do is to find out the latitude of lambda CA. So, what would the latitude of lambda CA be? Now, this is actually quite simple. So, as you saw from the first part, right, what is the latitude equal to? So, you can actually simply take it to be this angle, this length that we've got, which is the length here, right, length here divided by this particular axis. So, if it's the length divided by the hypotenuse, which is the actual length of length of the whole vector. So, lambda CA would simply be equal to sine inverse, right, of ZCA divided by omega A with respect to C, right. So, this will give us the value of the latitude. So, we know what the latitude would be. How about the longitude then? How do we find out the longitude of phi CA, right? This is the other thing that was important. And for this would become then same, just using basic trigonometry. This would be equal to YCA divided by XCA. the tan inverse of this particular angle. So using this, right, using just this simple Cartesian technique, right, we can actually calculate first of all the magnitude, right, of the velocity. You can calculate both the latitude and the longitudes of the latitude and longitude of the Euler pole of rotation for the plate boundary between plates A and C. So it means then that we have the complete information we need for calculating for all particular pairs of plates. Now, what does this actually mean? Using this technique, given the knowledge for any particular pair of plates, it means that the Euler pole positions and angular velocities for different plate pairs can be calculated. And as you can see, right, so this has been calculated for a lot of different parts here. So you can see that the plate velocity and Africa and Antarctica, between Africa and Eurasia, Africa and North Asia, for all of these, the positive pole positions, this is the conventional way of depicting it, and longitudes, these have been summarized together with their angular velocities. And these were summarized long ago by Demetz et al. In a 1990 paper. These have been modified with time, but not significantly. Now, there's just one thing to remember. The thing to remember here is that this tan inverse value that we calculate here, right, this would be, it's double valued. It's double valued in the sense that tan of theta is also equal to the tan of 180 plus theta. So if you get something like that, how do you know what the value of theta would be? So here, the most important thing that's important is the value of, say, xCa. What is this value? Now, if xCa is greater than 0, that is, if it is positive, then it is important to remember that the longitude phi Ca, right, it will actually have a value between minus 90 degrees and plus 90 degrees. So it will have a value, the magnitude of the value would be between this. If xCa is less than 0, right, if xCa is less than 0, then phi Ca, right, the magnitude of phi Ca, this will actually be, greater than 90 degrees. So this is the convention that you should keep in mind. So now, given this, as you see, we can calculate the pole positions, Euler pole positions, angular velocities for any plate pairs. And this has been compiled, right, and it's listed as you can see. This technique can be used to calculate the Euler pole positions and angular velocities for any pair of plates on Earth. So what you're doing is just using simple trigonometrical geometry. You can actually use vectors to simplify the calculations even further. Now, this is Demetz's paper from which the table I've shown you is compiled. And as always, use Fowler and Moore's and twists when you find any problem in understanding what's going on. So thank you till the next class.